Hello everyone, welcome to another lecture of the subject control system. In previous lecture we discussed about various types of standard function and their Laplace transform. There was this impulse function which Laplace transform of which was 1. For step function Laplace transform was 1 by s, and for ramp function it was 1 by s square, and for in general t to the power n ut it was n factorial by s to the power n plus 1. And for exponential function, that is e to the power at ut. Why this is ut? Because we were considering about from 0 minus to infinity. The integration was from 0 minus to infinity ft e to the power minus st dt. For the transformation we used this formula. And what is this formula? This formula is for Laplace transform of unilateral Laplace transform basically. So for unilateral Laplace transform, we only consider time axis to be 0 towards infinity. So what was there before t equals to 0, we don't care. That's why we multiply one ut here with the function, so that the portion of the function before t equals to 0 can be ignored. Okay. So similarly, for sinusoidal, sin omega t was giving you omega by s square plus omega square, and cos omega t ut was giving you s by s square plus omega square. Okay. So these were the transfer functions. These were the Laplace transform of different standard functions. Now today I'm going to do something, discuss some properties related to Laplace transform. Okay. So what are the different types of properties that are there in Laplace transform? So first of all, the first and foremost property was is the linear property. Okay, linearity property. So linearity property means the Laplace transform is basically a linear operator. That means, what is a linear operator? A linear operator or function, anything. What is linearity in general? Linearity means something that obeys superposition principle. What is superposition? Superposition means combination of two things. One is scaling, another one is homogeneity. I don't know whether my spelling is right or not, but it's homogeneity. I think it's this, whatever be the case. Okay, so what is homogeneity and what is scaling? Or you can call it, oh sorry, it's not scaling, it's scaling or homogeneity, and this one is additivity. Sorry, if you have one function f of x, if it is linear, then for some input x1 it is giving you f of x1. Now if you scale this input to by some factor a, then it will give you f of ax1, and this will be just scale of this output. Okay, scaled version of this output. This is called scaling property. Whenever you are scaling the input, the output will be also scaled by the same factor. And what is additivity? Now if x1 is giving you output as f of x1 and x2 is giving you output of f of x2, then x1 plus x2 together will give you output as obviously f x1 plus x2, which will be f of x1 plus f of x2. What does it mean? It means whenever you combine two different inputs, then the output of the two different output with respect to those different inputs will be combined to produce the output of the combined form. Okay, so if x1 is generating the output fx1, if x2 is generating output fx2, then x1 plus x2 will be generating output fx1 x2, fx1 plus x2, which is actually the sum of these two output, Okay, so this one is scaling and this one is additivity. Okay, homogeneity and additivity property. Now those functions which actually obeys these two principles simultaneously, those functions will be called as linear function. Now we are discussing about Laplace transform. So what is Laplace transform? Laplace transform is not a function but an operator. So here this operator will actually obey these two principles. So how it is going to do? Let's say you have some function ft and Laplace transform of some function of f1t, let's say. Okay, and Laplace transform of f1t is giving you of f1s, let's say. Now if you scale this function by some factor a, then the Laplace transform of a into f1t will be a into f1s. That means if you scale the time domain function by a factor a, then the frequency domain frequency domain corresponding to this function, that means frequency domain representation, will be also scaled by some factor a, by the same factor a. Okay, now again for f1t, if it is providing you f1 of s, capital F1 of s, and for f2t, if it is giving you capital F2 of s, then f1t and f2t together, f2t combinedly together will result f1s plus f2s. So Laplace transform obeys actually this homogeneity principle and additivity principle. That's why Laplace transform is called linear operator. Okay, so what is the use of these things? Let us see. So what you can write as the first property, Laplace transform of some function f1t scaled by a1, or let's say a, plus some function f2t scaled by a2 or b, let's say, then it will generate a of Laplace transform of this function f1s plus b of Laplace transform of this function, that means f2 of s. This is called linearity property. Okay, so what is the use of this these types of actually property? Like if you have given if you have been given basically a function, let's say ft equals to ut plus e to the power at ut, that means let's say the function is like this. Okay, the function is like this, 1 minus e to the power minus at ut. Okay, so how you are going to arrive to this Laplace transform domain? Okay, Laplace domain actually. So you can write it as ut minus e to the power minus at ut. So now that ft can be written as, this can be written as f1t and this can be written as f2t, isn't it? And or let's say, yeah, this can be written as f2t, and let's say a can be written as 1 and b can be written as minus 1. So what is the form here? So ft equals to a of f1t plus b of f2t, and it will give you ft. So the Laplace transform of this thing will be the Laplace transform of this thing equals to a into f1 of s, that means f1 of s is Laplace transform of f1t, small f1t, and b into f2 of s, and f2 of s is Laplace transform of second function, second time domain function. So now what is happening? Ut is having Laplace transform of 1 by s, and e to the power at ut is having Laplace transform of e to the power minus at, having Laplace transform of 1 by s plus a. So now the value of a is 1 here, so directly 1 by s, and the value of b is -1 here, -1, and f2 is 1 by s plus a. Now for understanding purpose I have done this simple calculations in a broad way, but whenever you look at the function, you can, just looking at it, you can convert it. Ut is having 1 by s minus e to the power minus at ut having 1 by s plus a, that's it. So using this formula you can easily calculate for such a combination of one or more functions. Okay, so this is linearity property. Okay, so what is the next property? The next property is time shifting. Time shifting. What does this property say? This property says if you have xt generating fs, then, or xs, or let's say this is ft, you are generating fs, let's say you have time shifted this function by some amount t naught. Now what is time shifting, what is time scaling, that things, those things will be actually discussed in a signal system, but as of now just remember, if you have some function and if you time shift, you will shift this function either in rightward direction or in leftward direction by minus t naught. If t naught is positive here, then it will be shifted towards right. If t naught is negative, that means if t naught is positive and the function is like this, then it will be shifted leftwards. Okay, but that is not our concern. We just need, if there is time shifting, then what will be the function value? F of s into e to the power minus s t naught. Let me see. Yeah, f of s into e to the power minus s t naught. So now again, what is the use of these kind of things? Let's say you have given one function like t to the t minus 3 whole to the power n u t minus 3. How we are going to obtain the transfer function? Look, you know what is t to the power n, let's say not general, let's say this is 2, okay, t minus 3 whole square u t minus 3. So you know the Laplace transform of this thing, it is n factorial by s to the power n plus 1. Now the value of n here is 2. So what is the value of t square ut? That is 2 factorial by s to the power 3, that means 2 by s cube. T square ut will give you 2 by s cube. Now this is ft and this is fs. Now actually my function is t minus 3, that means my function f of t minus t naught, f of t minus t naught is this, that means my value of t naught is actually 3. Okay, so what will be the function? F of s into e to the power minus s t naught. So what is f of s? F of s is 2 by s cube, and what is t naught? E to the power minus s, that means minus 3s. Okay. So the Laplace transform of this function is giving you this using time shifting property. Okay, look, this kind of properties are so much helpful in order to actually, in order to simplify the calculations for calculating Laplace transform, or even in inverse Laplace transform also. Okay, inverse Laplace transform will not be discussed in this lecture, but whenever I will discuss inverse Laplace transform, then you will see that these properties will be helpful. Even in Laplace transform, that means from for transforming from time domain to frequency domain, also it is helpful. Okay, so what is time shifting? Time shifting property is if ft A is giving you Fs, then f of t minus t naught will give you f of s e to the power minus s t naught. Okay. Now there is something frequency shifting. Okay. Frequency shifting. What is frequency shifting? Okay, let me write it here. This is linearity. This is time shifting. This is frequency shifting. Okay. So what is frequency shifting? Frequency shifting can be written as, look, what is time shifting? Time shifting means the time domain function will be shifted by amount of t naught in rightward or leftward, that I don't know, but it will be basically shifting. Now what is frequency shifting? Now frequency shifting is frequency domain function will be shifting. Okay, that means if ft is your time domain function, then time shift means f of t minus t naught or t plus t naught, whatever. So if it is frequency shifting, that means the shifting will be in frequency domain. That means fs will be shifted by f of s plus a or f of s minus a. Okay, so how that is going to be done? That means if there is time shifting in time domain function, then frequency domain function will be multiplied by some exponential, and the exponential will be, if it is t minus t naught, then the exponential will be e to the power minus s t naught. Okay, this minus will reflect here. Okay, now for frequency domain, now the things will be just opposite. That means for shifting in time domain, we introduce an exponential function in frequency domain. Now we are interested in shifting in frequency domain, so we will introduce one exponential term in actually time domain. So now what is the thing is, if ft, again ft is giving you fs, this is the fundamental condition. Now if ft is multiplied with some exponential function e to the power at ft, okay, if it is instead of ft it is e to the power at ft, then the function will be shifted. F of s will be actually f of s minus a. Now one thing that to be noticed here, if time domain function is shifting towards, that means t is replaced by t minus t naught, then one exponential of minus s t naught will be multiplied. But in frequency domain the thing is opposite. That means if in time domain e to the power plus at is multiplied, then in frequency domain it will be s minus a. Okay, and if it is e to the power minus at ft, then it will be s plus a. I hope it is clear. Okay, now can you remember one formula for this? That means which actually one formula you have already have in your hand, and that formula actually verifies this property. Okay, you had ut, the Laplace transform of ut is 1 by s. You had e to the power at ut, the Laplace transform of this one is 1 by s minus a. So look, if ut is ft, then fs is 1 by s. Now if this ft is multiplied by e to the power at, then the frequency domain signal is shifted by amount of a, that means f of s minus a. Now if it is f of s, this is f of s minus a, isn't it? What is f of s minus a? In fs, wherever there is s, you replace it by s minus a. That's it. E to the power at ut is giving you this. So actually if e to the power at ut we use as standard function, but actually this is the result of this frequency shifting property. Okay, so what is frequency shifting property? If exponential term is multiplied with the function ft in time domain, then the frequency domain signal will be shifted based on the exponential term. That means if e to the power at ut at ft, I was writing it right, okay, e to the power at ft, then it will be f of s minus a. Now if it is, let us generalize this one, e to the power plus minus at ft, it will give you f of s minus plus a. That means whenever plus at it is minus a, whenever minus at it is plus a, okay, and provided ft provides fs, ft results fs, and so e to the power plus minus at ft will provide f of s minus plus a. So this is frequency shifting. Now there is another one, that is time shifting. Okay, sorry, time shifting was done, it is time scaling. Now what is time scaling? Time scaling is basically this time will be scaled by some amount, okay. Now if you have ft which is giving you fs, again this is similar. Now if you actually scale this time, not the function, it is not the amplitude scaling, this one is amplitude scaling, a is multiplied everywhere in the function, it is not that thing, it is rather it is rather f of at, that means the time is scaled by a factor a. So what will be the frequency domain representation? It will actually f of s minus a, but not only this portion, 1 by a will be multiplied, okay. So again you have some you can have some actually, you know, some example like this. If you have rt equals to, let's say if it is giving 1 by a square, so if you are giving you are given r of 3t, then it will be simply 1 by 3, 1 by s will be replaced by s by 3, s by 3 whole square, that means 1 by 3, 9 by s square, that means 3 by s square, okay. Like this. This is time scaling. Time scaling. Now there is another one, that is multiplication by t. Yeah. What is multiplication by t? If you have ft giving you fs, then you are copying these things. You need to remember these properties. Okay. Now because mainly, okay, let me tell you, mainly these three things is used, and there is something differentiation property and integration property. These 5 properties mainly used are mainly used, okay. Now time scaling multiplication by t actually not used much, because we don't need that thing, but still we need to know these things, because question can be come with this property, okay. Multiplication by t. What is multiplication by t? ft is giving you fs. Now if you multiply ft by t, the frequency domain, that means the Laplace domain representation, will be the differentiation with respect to s, but with a minus sign, okay. I hope it is clear. Now can you remember one thing? What is the function ut? Okay, what is rt? Rt, can you represent rt in terms of ut? Yes, it is tut. Now ut was giving you 1 by s. What was rt giving you? 1 by s square, isn't it? So Now RT can be replaced as TUT, so it is multiplication by T of this function. Now UT is giving you Fs equals to 1 by S. Now this one is minus dds of 1 by S. So minus dds of 1 by S is minus 1 by S square, 1 by S square. TUT is giving you minus this is plus 1 by S square. This is RT plus 1 by S square. Actually these standard functions are derived by this formula only, okay, by these properties only. So we need these standard functions so much, that's why we discussed it earlier, but we need to know the properties. And look, this property actually results the same function we actually discussed in the standard functions chapter, okay, standard function topic. So this one is multiplication by T. Now there is another two major property, that is differentiation property. Differentiation. What is differentiation property? If you have Ft as Fs, then differentiation of Ft, I have discussed it earlier while discussing Laplace transform, while discussing transfer function, because from differential equation we need to arrive to the transfer function of any physical system. There I discussed about this differentiation property. So the differentiation of Ft is resulting f of s into f of s minus f of 0. Yeah. Or you can say it f of 0 minus the initial condition. Okay. Now if it is second time differentiation, d2ft dt 2, it will give you s square f of s minus s f of 0 minus f dash 0 minus sorry, f dash 0 minus. Now after differentiation, now I discussed it about nth time differentiation, it will be s to the power n fs minus s to the power n minus 1 f of 0 minus up to 0 s to the power 0 f of n minus 1th derivative of 0 minus. Okay. This was the thing, differentiation. And there, look, one similarity between multiplication by T and differentiation property. Now whenever you are multiplying the time domain function with a factor T, then the frequency domain function is actually differentiated. Just forget about the about this minus sign, some differences will be there, but the thing is, whenever you multiply the time domain function with the factor T, then the frequency domain function will be differentiated. Now whenever you differentiate the time domain function ft, then the frequency domain function will be multiplied by some factor s. If you consider the actually initial conditions to be 0, then as tft is resulting minus dfs ds, similarly dft dt is resulting s of fs. It's a very nice actually symmetry between time domain and frequency domain. Whenever time domain signal is multiplied by t, the frequency domain signal will be differentiation. Whenever differentiation actually time domain signal is differentiated, the frequency domain signal will be multiplied by some factor s. Okay. Now if initial condition is 0, then only this thing will be true, otherwise there will be initial condition. And in case of multiplication by t, the differentiation will be along with some negative sign. Okay, so this is a kind of similarity between time domain and frequency domain and the Laplace transform. Now the next thing is integration. What is integration property? If ft, similarly the starting is same in every property. If ft is giving you fs, then what will happen if there is some integration minus infinity to t f of tau d tau, this will give you f of s by s. Okay. Now just remember one thing, if time domain function is differentiated, then s will be multiplied with fs. If time domain function is integrated, then s will be divided by fs. Okay. Sorry, fs will be divided by s. So these are the properties, the main properties. These properties and this linearity, this time shifting and frequency shifting, these 5 properties are of major importance, but time scaling and multiplication by t can be used somewhere. The problem can be framed like this, that you need to use these 2 properties, but most of the cases in a practical scenario, in actually practical scenario, to design control system and to design any kind of system, we mainly need these 3 and these 2 properties. Now among these properties, this property and this property, that means differentiation property and linearity property, is the most used property. Why? Because no signal, no system can be having some single function. That will be sum of some complex functions. That means some f1 will be there, some f2 will be there, and it is not stopped here. If there is some c into f3t, d into f4t, it will reach up to infinity. It can reach up to infinity. There are n number of functions, then there will be n number of terms in the frequency domain representation. Okay, so whenever you have signals or systems which is some complex signal, that means some combination of some individual signals, then this property is used so much. And in practical case, this is the case. You will have in practical scenario the combination of various types of individual functions. So you need to use linearity property. And for designing of system, as I said earlier, you need to arrive to the transfer function, and the transfer function, the first step of the transfer function is the differential equation. The physical laws will give you the differential equation, and without differentiation property, you cannot convert the differential equation into transfer function. So these 2 property, linearity property and differentiation property, is of the most important. After that, time shifting, frequency shifting, and integration property is important. Then at the last comes time shifting and time scaling and multiplication by t. Okay, so these are the different types of properties. There is something I said in the previous lecture, that there is initial value theorem and final value theorem. I will discuss in the next lecture, but in this lecture the time is not permitting me to do that thing, so I'm postponing the discussion of inverse Laplace transform and initial value and final value theorem. Those main 3 things will be discussed in the next lecture. Okay, so I'm not erasing it, just let it be here. So what we have learned today, we have learned total 7 properties. Okay, 7 properties, that is linearity property, time shifting property, frequency shifting property, time scaling property, multiplication by t property, differentiation property, integration property. After this we will go for inverse Laplace transform. There is another integral formula of inverse Laplace transform, but again just like the Laplace transform, as we don't use the integral formula so much in real life, We will not use the integral formula for inverse Laplace transform in real life again. Based on some, we will actually, there is a concept called partial fraction. Using partial fraction, we actually can convert the complex Laplace transform system, that means the complex Laplace domain representation, into some simpler one, by which we can actually convert this into some summation of some standard functions or standard Laplace transform functions. Okay, and then from that we can arrive to the standard functions in time domain, and that will be easier uh, than actually computing the integral. Okay, so that is the thing. And initial value theorem and final value theorem, as I said, you don't need to convert every time the Laplace domain into frequency the Laplace domain into time domain. You don't need to convert every time, because it is a kind of tedious work. For some degree of from some degree of, let's say, for 2 degrees or even 3 degrees is enough for us to compute the inverse Laplace transform manually. Nowadays computers are used to convert the Laplace domain into time domain, so that is not a tough work. But the thing is, whenever you are calculating the you are converting the Laplace domain from the converting the Laplace domain into time domain, then actually you need to do a lot of things. Like, you need to first have to convert it into partial fractions, then you need to do a lot of stuff. That's why what we do is, sometimes you may have some Laplace domain representation and you need to know some value in the time domain function. Like, this is mainly 2 values, that is the final, that means the final value of the time domain function and the starting value of the time domain function. But this initial value and final value theorem says that you don't need to compute the time domain from Laplace domain. By staying in Laplace domain also, uh, you can calculate the value at time domain. That is something interesting, so we will see that in the next lecture. So okay, this much for today's lecture. Thank you.